Now that we're looking at file systems, we're going to take a look at how disk drives work. And you might be saying, like, why should we look at disk drives? I mean, nobody uses those, everybody uses SSDs. But in reality, disk drives have been the design point for file systems for about 40 years. And you will see that there are decisions we make when we build file systems that are still designed around the idea that you've got spinning media underneath. And so what are the characteristics of this spinning media that dictate how we build file systems? So in order to get there, let's look at how disks are integrated into our system. So until now, we've shown you the standard picture where we have cores and they talk to memory. Now, in reality, in order for a processor to talk to memory, it's got a piece of hardware in it called a bus interface, because this connection to memory is really a bus. Now, we've drawn it as like one straight line, but in fact, what you really have is you have a bus that crosses something called an I/O bridge, because the processor has to talk not only directly to main memory, but it also needs to talk to devices. And so we split this bus into the system bus and an I/O bridge. And so we have a system bus that talks from the processor to the bridge, and then we have a memory bus that talks from the bridge to memory. So you might imagine that in order to talk to I/O, we need yet another wire, which is an I/O bus, and that's what we're going to use to talk to our devices. So data is going to flow either directly across the bridge to memory, or sometimes it might flow over the I/O bridge and onto the I/O bus. And then between the I/O bus and our devices, we have something called a host bus adapter, which is that devices speak their own protocols, and we sort of need to translate those protocols back and forth across the buses. All right, so that's how we're integrating storage into our system. And it doesn't matter if this is a hard disk or an SSD, it still talks on the I/O bus. And that's really the key difference between devices and memory. You might have heard people talking about new NVRAM or non-volatile memory. And what's exciting about that is that while you can take it and package it into an SSD and put it here as an I/O device, you can also just put it directly on your memory bus and it looks like memory, and yet when you turn power off, the data sticks around. So this is what's called this new non-volatile memory. And rather than having to access it over the I/O bus, you can access it just like you do main memory using load and store instructions. But we're not going to talk about that. We're going to focus on drives for now. So we typically draw a picture of a disk drive as like this cute little box. But inside the drive, what you really have are a collection of platters. And each of these platters are, they look like what you might have seen as old DVDs, right? So they're a platter, they're often very shiny, and they're covered with a magnetic surface. If we then look at those platters in a little more detail, a platter has both a top and a bottom surface. So you can write data on both of the top and the bottom surface. The platter themselves are divided into tracks. And so you can think of tracks as just concentric circles. And so what's important to realize is that these are called disks and they spin. So we write data on the surface of the device. And if data is laid out contiguously around one of these tracks, then we get to read it while the disk is spinning. Okay, so data that's laid out in a single track is sort of good because while the disk is spinning, we can just slurp that data off. We then divide these tracks into smaller units called sectors. And a sector in the old days used to be 512 bytes. Today, sectors are always at least 4K. And when we talk about disk blocks, what we're really talking about are these sectors. Okay? So we can read multiple sectors as the disk spins, as long as they're in the same track. Now, what if they're in different tracks? Then what happens? Well, now we need to understand, how do we read and write disks? So it turns out that the way we read and write disks, that there's mechanical devices, right? So there's a big arm. So here's your disk, it's spinning, and there's a big arm, and the arm has these things called the read heads or the write heads. Okay, so that's what this is showing. So here is a mechanical arm that can move back and forth along the disk. And what that's doing is it's taking these disk heads. So what we're looking at the disk sort of horizontally. And so these correspond to the tracks on the disk. And what we do is we move the disk heads over the disk to get to the correct track. And these heads, this is a magnification, right? These heads fly really, really close to the surface of the disk. So if you've ever heard the term disk crash or head crash, what that means is that something terrible happened, like a gigantic particle of smoke got into your disk drive and it caused that head to crash onto the disk surface. And as you might imagine, that's a really bad thing, right? So if your disk heads crash, what it typically does is it just scrapes the magnetic coating off the disk and you've lost data. So that's what a head crash or a disk crash really is. Now, the important thing here is I keep emphasizing this like mechanical disk arm. So as soon as I say mechanical, as opposed to like digital circuit, you should think slow. And that is really, really true. So the reason disks are so much slower than other things is because in order to read data, you've got to move the arm to the right place, and then you've got to wait for this disk to spin around. So when we talk about the performance of disks, we talk about it in two pieces, okay? There's the time it takes for the disk arm to move to the correct place on the disk, and that's called the seek time. And then once we've moved to the right place, we actually have to wait for the right data to get underneath the head, and that's called the rotation time. So disk access time is measured in terms of seek time and rotation time. Now, if you're reading a whole track from the disk, like the whole circumference, that's great because you pay the seek time, and no matter where you start, you can kind of slurp all the data and then deliver it, and you can figure out like where's the first one. So whole track reads are really good, but reading individual disk blocks can be really slow because you're going to pay a seek, and then on average, you're going to pay about half a rotation to get to the correct data. Now, because it's advantageous to lay things out along the same track, when we number the sectors on a disk, we actually number them so that if you lay things out in sort of a numbered contiguous fashion, the disk will behave well. So the way we're going to number these platters, or I'm sorry, the sectors on each platter, is that we usually start at either the top or the bottom, and we start in the outermost track, and we just label, so this would be 1, and then 2, then 3, and so we label around a track. And now you might think that the next thing you would do, you would then go to the next track. But in fact, moving to the next track on the same platter would require a seek of the head. So instead, where's the next closest block? It's on the bottom of that platter. So what we do is we go around one track on the top of the platter. Then we go around one track on the bottom of the platter. And then we go to the next platter. So what we do is we number around a single track, underneath around the track. Then we go to the next platter and we do the same thing. So contiguous blocks on the disk are what we call a cylinder, which is a single track stacked through all the platters on both sides. And so the very fastest performance we'll get is if we're reading like entire cylinders, because we get to read all those data on some number of rotations without ever moving the head. Okay, and moving that disk head is what's really expensive. Rotation is also expensive, but if we're getting data while we're rotating, that's like useful work, right? The disk is spinning and we're sucking data off it. So that's like good work. When we're moving the head, we're not getting any data. So that is just pure overhead. So now to put this in a little bit of historical context and also to give you a sense of how fast or slow these things are, here's some disk performance data. So typically today, when we talk about disk drives, most of them will spin at a rate of approximately somewhere between 7,200 and 10,000 revolutions per minute, right? Now, as soon as I say per minute, you should be going, wait a minute. Like we've been talking in terms of like picoseconds and nanoseconds, and now we're talking in terms of minutes. So that's huge, right? Now, yes, there's a lot per minute, so you can reduce it to how many rotations per second, but it's still so many orders of magnitude difference that you should be going like, wow, that's really slow. Okay, so that's a canonical rotation speed. Seek times are in small numbers of milliseconds. Okay, so again, milliseconds, 1,000 to a second, instead of our nanoseconds, which are like billions to a second, right? So again, many, many orders of magnitude. Now, the one place where disks excel is in density, right? How tightly can I pack bits? And so while with processors, what we've been seeing over time is that they get faster and faster and faster. We see less of that in disk drives, but we see that they hold more and more data. And so when you look at the evolution of storage, right, what we're seeing here is a timeline along the bottom and the typical capacity of a drive. And what you see is that we get kind of exponential growth in capacity, but that is not mapped with an exponential growth in performance. Okay. And so this is basically showing the areal density, like how tightly can I pack the bits on the disk? And so in persistent storage, it's often like, how tightly can I pack the bits as opposed to how quickly can I get them? Now, there is a correlation there, because if I take the same size disk and I can spin it at the same rate, but I can pack the bits more closely, then for every revolution of the disk, I will in fact get more data. So my transfer time, or the time I can read a track, will in fact get better. Or I'm sorry, the time to read a whole track won't get better, but I'll get more data for it. So the bandwidth that I'm getting off the device is better. So what we see in persistent storage is small increases in performance, but these sort of exponential growth increases in density. Whereas with processors for a long time, we got to see both an improvement in density and performance. These days, with the end of Moore's law and Dennard scaling, we're not seeing quite that performance improvement that we used to see. So what we're seeing is another kind of density, which is that we're packing more cores on a single chip.